Hey everyone. In the last episode, we introduced the notion of the expected value of a random variable. Today and in the next few episodes, we will study expectation and practice with it. We will see a lot of beautiful examples. But first, let's recall. A random variable, usually denoted by capital X, Y, or Z, is a function on a sample space. In other words, a random variable assigns each outcome a number. For instance, if you flip 3 coins, the number of heads is an example of a random variable. In particular, if you flip head, tail, and then a head, then the random variable assigns this outcome the number 2 heads. A random variable can take on many values, such as here 0, 1, 2, 3. But there is one single value that best describes the random variable. It's called the expected value, or expectation of x, or sometimes the mean of x. It's denoted E of x, and by definition, it can be computed by multiplying every value, little x, that the random variable can take, such as 2, by the probability that the random variable takes that value, and then we sum over all values. Let's notice some simple but useful properties of expectation. Suppose a random variable x takes the same value, let's call it a, with probability 1. For instance, you ask people in the street, how old are you? And they always respond, 18. What's the expected value of the age then? Well, it's going to be 18, because the random variable is 18 deterministically. So the expected value should be a in this case. And to see this, just apply this formula. So the sum will consist of a single term, a, times the probability that x equals a, which is 1, and we get the result. An extremely important property of expectation is linearity. What happens if I multiply every value that the random variable can take by 10? What will happen to the expected value? Well, the expected value will also blow by the factor of 10. Also, if I add two random variables, one with expected value 3, the other with expected value 5, what will be the expected value of x plus y? Well, it's going to be 3 plus 5, which is 8. Generally, the expected value of ax plus by equals a expectation of x plus b times expectation of y. Let's give an informal proof of this theorem for discrete random variables. So suppose x can take on values x1, x2, x3, and so on, with probabilities p1, p2, p3, and so on. And suppose that y can also take some values y1, y2, y3, and so on, with probabilities q1, q2, q3, and so on. Then ax plus by can only take values axi plus byj. And that happens if x equals xi and y equals yj. Let's denote this probability by pij. Great. So how do we compute the expected value? By definition, we need to sum the values that the random variable can take multiplied by their probabilities over all values, over all I and j. Let's split this sum in 2. Now a is a constant, so we can pull it out of the sum. Inside the sum, let's first sum over i's and then over j's. And we do similarly for the second sum. But this time we sum first over j's and then over i's. Now, what is this sum? It is the sum of all such probabilities. And this sum equals p of x equals xi. Let me show you why. This is the event where x takes value xi. On that event, the random variable y can take on different values. For instance, this is a part of that event where y takes value y1. On this part of the event, y takes value y2, and so on. Now, if you sum the probabilities of all of these parts, which are mutually exclusive, we get the probability of the entire event, which is x equals xi. So again, this sum the sum of all these probabilities, is just the probability that x equals xi, which is pi. And similarly, this is qj, check it. So we get a times the sum xi pi plus b times the sum yj uj. And by definition, this is the expected value of x. It is the sum of all values x can take times their probabilities. And similarly, the other term is expected value of y. And we proved the linearity. Also, I was a little sloppy in one step of this proof around this equation. It only happens if all of these numbers are distinct. Think about how to correct this proof. To recap, we proved that if we add two random variables, the expected value of the sum is the sum of expected values. Once we know how to do it with two random variables, we can add the third random variable and the fourth, and so on and so forth. So by induction, the expected value of the sum of any number of random variables is the sum of expected values. And now, a lot of examples. Let's revisit the example where we flip the coin 3 times and a random variable x is the number of heads. Let's represent x, the number of heads, as a sum of 3 random variables, where x1 is the number of heads in the first flip. It could be either 0 if you flip a tail, or 1 if you flip a head. And x2, similarly, is the number of heads in the second flip. It is also either 0 or 1. And x3 is the number of heads in the third flip. Summing these 3, we get the number of heads in all of the 3 flips. By linearity of expectation, expected value of x is the sum of these expected values. Let's compute the expectation of each. x1 is the number of heads in the first flip. So x1 can take on only 2 values, 0 and 1. What's the probability that x1 is 0? That's the probability that the first flip was not a head, was a tail. That is 1/2. And the probability that x1 is 1, this is the probability that the first flip was a head, is also 1/2. So by definition, expectation of x1 equals 0 times 1/2 plus 1 times 1/2, which is 1/2. Similarly, you compute the expected value of x2, and it is also 1/2, and expected value of x3 is also 1/2. So the ultimate result is 3 times 1/2, or 1.5, and that's the answer. Example 2 is a famous St. Petersburg paradox. Imagine I offer you to play the following game. There is a pot, and the initial stake, the money in the pot, is $2. Now you toss a fair coin, and if you flip a tail, then the game ends, and you win whatever is in the pot, which is $2. But if you flip a head, the stake doubles. I replace the $2 by $4 in the pot, and the game repeats. You again flip the fair coin. So these are the rules. How much are you willing to pay me to play this game? What would be a fair price to enter this game? How can we formulate this question mathematically? The fair price to pay the casino should be the same as your expected winnings. Then you'll be even. So the question is, what are your expected winnings? Let x be the player's winnings, and we would like to compute its expected value. Here are all possible scenarios that can happen in this game. Either your first toss was a tail and then the game ends, or you toss head and then a tail, or head, head, then a tail, or head, 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 and a tail, and so on. If your first toss was a head, your winnings are $2. And the probability of that, the probability of tossing the tail, is 1/2. If you toss head and then a tail, the stake doubled, so you go home with $4. The probability that you toss HT is 1/4, because there are 4 equally likely ways to toss 2 coins: HH, HT, TH, and TT. if you toss HHT, then the stake doubled twice, from $2 to $4, from $4 to $8, and you go home with $8. The probability that you tossed HHT, one of the 8 equally likely outcomes, is 1/8, and so on. So players' winnings can take value 2 with probability 1/2, 4 with probability 1/4, 8 with probability 1/8, and so on. Therefore, the expected value of x, by definition, is 2 times 1/2 plus 4 times 1/4, 8 times 1/8, and so on. Now this is 1 plus 1 plus 1, and so on. So we're summing ones infinitely many times, and the result is infinity. So you are expected to win an infinite amount of money. As a result, the fair price to enter this game is infinity. In other words, you should pay any price to enter this game. It is very disturbing, isn't it? What's your feeling? I would say maybe $2, maybe $3 would be a fair price to do that. No more than $10. There are many explanations of this paradox, and I'll encourage you to read about them. One explanation is that this game is extremely unstable or volatile. You get bigger and bigger sums of money, but with smaller and smaller probabilities. It's like a bubble. You bet on a huge amount of money, but with very, very low confidence. This phenomenon is similar to volatility of financial markets. Another explanation of this paradox is that maybe the notion of expectation is not suitable for this problem. The expectation is driven up by events that have very, very small probability. The expectation is fooled. A more stable notion, less volatile cousin of expectation, is the notion of a median of a random variable. It's defined as a number, m, that breaks down the sample space into 2 equal parts. The probability that the random variable is less than m, and the probability that the random variable is larger than m should both be 1/2, or at least 1/2. A number m that makes both of these inequalities true is called the median. Let's compute the median of the winnings. If we draw a line here, then this probability is 1/2, and this probability, if you sum all these numbers, is also 1/2. So in this game, the median, which is not uniquely defined, the median of winnings is any number between 2 and 4. So the message is, a fair price to pay the casino for entering this game would be somewhere between $2 and $4, which is much more intuitive. And that's another resolution of this paradox. Read more about it and stay with me for the next episode. See you.